Hello, everyone. Today I'm presenting our recent work titled Improved Generalization Bounds for Communication Efficient Federated Learning. I'm Payman, a PhD student in electrical and computer engineering at University of Illinois, Chicago, and this work has been done under the supervision of Professor Sefroglu. She's also a co-author of this work. Let's start with our table of contents. First, we'll go over the introduction. Next, we'll discuss the problem statement. And in the third section, we'll present the improved generalization bounds. Then we'll introduce an algorithm called FedALS, which is based on the generalization bound analysis. Finally, we'll review the experiments and conclusion. We all know that in federated learning, communication is the major bottleneck, and this is even more severe with large language models. There are actually two solutions for this. One is doing local SGD, and the other is doing mini batch SGD. Now, because in local SGD we are moving toward the optimum while computing the gradients, it is more effective, and practical studies have also shown that local SGD is a better choice. The purpose of communication in federated learning is to reduce the consensus distance among clients. So, what do we mean by consensus distance? It is basically the average difference between each node's model and the average of all models among all clients. This is actually the squared second norm distance. Having a small consensus distance during the optimization helps us move forward to the global optimum at a faster rate. So, we ran an experiment to measure the consensus distance while training a ResNet 20 model on CIFAR10. And we found that in the early layers, the consensus distance is smaller compared to the final layers. This actually hints us that we might not need to do as much aggregation for the initial part of the model. There is a lot of research on representational learning that shows a model can be split into two parts. The first part is the representation extractor, which is actually a more complex part and pulls out the features from the data. The second part takes those features and turns them into the final output labels. This part is usually just a few fully connected layers and isn't that complex. These observations gives us the idea that initial layers, which are more similar, might not need to be aggregated as often. This could make the communication in federated learning more efficient, and also there are several studies have shown that federated learning with multiple local steps can actually learn a more generalizable model and works really well with non-ID dataset. This whole thing motivates us to investigate how local updates affect the model's generalization. Now we will talk about the problem statement. We have k clients, and each client has a local dataset as k with nk data samples. The dataset across all the nodes is defined as S, which is basically a set containing all the local datasets. Our model, M, parameterized by theta, is actually the output of the federated learning algorithm that takes the whole dataset as input. We define the empirical risk on dataset as the average of the empirical risks of each node k. There is also this notion of curly k of k, which is actually the weight of node k's local loss in the global loss. Then we have the population risk, where the data comes from the real distribution, and we take expectation over the data sample. The generalization error on the dataset S is defined as the difference between the empirical risk and the population risk. And finally, we have the expected generalization error, where the expectation is over the global dataset S. So let's take a look at our first theorem about the one-round federated learning generalization bound. Essentially, it says that if the loss function is strongly convex and smooth, we get the following bound for generalization. As you can see, the bound has two terms. The first term in the first line of equation 1 is based on the expected local generalization of each node. The second term is determined by how non-IID the data is across different nodes. And for non-IIDness, we define delta K and A for dataset S. This is basically the difference between the local empirical risk of node K's data on the federated learning model output and the empirical risk of node K's data for its own local model before averaging at the end of the round in federated learning. So you can see that if this difference is large, it indicates that the global dataset is quite different from the local dataset, and it shows the level of non-IIDness among clients. So here are the main takeaways from the theorem. First, for IID setting, where the second term disappears, we see a dependency on each model's local generalization with curly k of k squared. So this curly k of k is the weight we put on node k's local loss in the global loss. In the conventional case, where we assume the weights are uniform across all nodes, we have 1 over k squared. And this is an improvement over the current state of the art, which is 1 over k. And also, we can see that for non-IID datasets, we have the expected generalization bound that doesn't necessarily improve with averaging. Now, let's move on to our all-round generalization bound. We define ZKR as the union of all BKRT for t from 0 to tau minus 1. Here, BKR and t represents the batch of samples used in local step t of round R at node k, and we have t ranging from 0 to tau minus 1, which is the number of local steps in one round. We also define the empirical risk as the average of the empirical risks over all rounds. And similarly, we define the generalization error as the average of the generalization errors for each round. And we also assume that the gradient variance is bounded. This means that the variance of the gradients for each local dataset is bounded with some constant like sigma squared. So if these assumptions hold, we will have the following result for slightly convex and smooth loss functions. And here we have one additional assumption, that the data points used in round R, in other words, ZKR for all K, should be sampled without replacement. The bound here again has two terms. The first term is related to generalization of nodes locally, and the second term relates to non-IIDness. In the first term, we will see the complexity of the model class, as shown here with curly C of m theta. And now let's talk about the takeaways from this generalization bound for our round federated learning. Remember, in representational learning, we split the model into two parts. The first part, m phi of x, extracts the representation, and the output of this part is then fed into the head of the model. The head is actually much simpler compared to the feature and representation extractor. Our key intuition here is that we can reduce the aggregation frequency of M5, which leads to a larger tau and ZKR, and hence a smaller generalization error for the representation extractor. But here we need to consider that we can't just reduce the aggregation frequency of the first part of the model arbitrarily, because it will increase the empirical risk and affects the empirical risk optimization adversely. In the literature, the bound for the convergence rate of the empirical risk is provided, and it shows that as we increase the number of local steps and decrease the aggregation frequency, the convergence rate will degrade. And I'll point this out later on the slides in the experiment section. Now, here we have the main idea of our new federated learning algorithm called FedALS, which stands for Federated Learning with Adaptive Local Steps. The core concept here is to maintain a uniform generalization error bound across both components of the model. We've introduced a new parameter called alpha, which is the ratio of the number of local steps we perform for the representation extractor part of the model to the number of local steps for the head. And this is called the adaptation coefficient. We know that this adaptation coefficient should be larger than 1 because we want the same generalization for both components of the model. And note that the representation extractor is more complex, so we need more local steps for that part to maintain a uniform generalization. And this is where we get our communication efficiency from. And on this slide, we have a figure from one of our experiments that shows how well this upper bound is. We use a synthetic dataset for this because we needed to access the real distribution that the data samples are coming from. In the figure, you can see that the darker blue curve represents the generalization upper bound, and the light blue curve shows the actual generalization. And as you can see, the upper bound gets tighter as we increase the number of clients. Here we see the improvement of FedALS compared to federated averaging and scaffold as the baseline. We used ResNet20 as the dataset, as the model, and SVHN as the dataset. As you can see here, FedALS improves the final accuracy achieved, which can be attributed to the improved generalization from more local steps for the representation extractor. Note that in IID dataset, the improvement is slight because our generalization bound, the IID generalization, was already tight. Remember, it had only one term, and the second term wasn't there. We actually achieved similar results across different datasets and models. Here, you can see the result for CIFAR 100 and ResNet 20, which are consistent with what we saw in the previous slide. We also tested with large language models using OPT 125 million on multi-NLI dataset. Again, we observed improved generalization by doing more local steps for the representation extractor. Now, let's consider the role of alpha and communication overhead. As we increase alpha, communication efficiency improves. And in the table, you can see that as we increase alpha in the first column, the number of communicated parameters decreases in the last column. However, we notice that as we increase alpha from 1 to 100, we see accuracy improves up to a certain point, which here is alpha equal to 10. Beyond that, actually accuracy starts to degrade, even though communication efficiency still continues to improve. And that's because that increasing alpha up to a certain point is beneficial for generalization, but beyond that point, it starts to hurt the empirical optimization problem, reducing the overall effectiveness of the generalization and causing the results to drop. In another experiment, we looked at the effect of different combinations of phi and h. We used ResNet 20 as a model and split it like this. The first L layers are phi and the rest are considered as the head. Here we see that the most effective division is having the first 16 layers of ResNet 20 as phi. This shows that our theoretical analysis holds up, and deciding how to choose the representation extractor can be treated as a hyperparameter. So to wrap things up, we've characterized the generalization error bound for federated learning in terms of local generalization and non-IODness. And we've shown that less frequent aggregation can actually help with generalization. And this led us to develop an algorithm called FedALS by increasing the number of local steps for the initial layers and doing more averaging for the final layers. And we were able to improve overall performance in comparison to baseline. And that was it. Thank you for listening.